Okay, welcome to your Wednesday, October 22nd lecture. This one's pre-recorded. We should be able to be back on Zoom on Friday and then next Monday, so let's remind you of the schedule. So today, by the way, all the recordings are available in Brightspace. Today we're going to talk about independence. If you've looked at your web work problems, you might have noticed some questions about sets that are independent or not. We'll talk about that today. And then on Friday and Monday, we'll have Zoom lectures. It should be live. Unless something goes wrong, I'm having surgery tomorrow, but on Thursday, unless something goes wrong, we should be able to do Zoom lectures on Friday and Monday. I just can't get to campus. Those will be live, but we'll still post the recordings. And we'll go over the last material that you'll need for this test. Things like basis and dimension. You might have noticed some of those questions on the web work. And then we can dedicate, by the way, that's a lot of time to cover those topics. Oops, sorry. That's a lot of time to cover those topics. I've removed some of the material because of the fact that some people told me it's a little harder to learn with recordings and Zoom lectures. So I did, and I will make the exam will be next Friday. Yeah, oh, sorry. I mentioned Wednesday will be for review, and then next Friday, not this Friday, but in 9 days, this is October 31st, will be your exam. Okay, like I said, I'm pulling back the material a little bit, so it's not quite as complex as it might have been in a normal semester. And I should be back after that in person, back to normal. I might be hobbling with a brace on, but we'll see. Okay, so thanks for bearing with me. And all right, so today we want to talk. How about this? Let's start with a quick review of what we covered the last time, even though the recording is available to you. So let's just talk about what we covered last time. The big idea last time was span. Oh, by the way, in these videos, you should be able to adjust the speed, the playback speed. You can speed it up if it's too slow for you. If you're getting stuck, you can always pause it, take more notes, think about things. Okay, so I'll go faster than I do in a normal lecture. I'll try to. All right, so span. Remember the definition of span? It's a small word, but it has an important definition. The span of a set is the set of all linear combinations. All possible linear combinations is the important thing. So let's start with a quick example to remind us. If I took the span of the two vectors 1, 0 and 0, 1, that would equal k1 times 1, 0 plus k2 times 0, 1. That's literally what a linear combination is, in case you don't remember that. Linear combination is just where you add things together, but you first can put their own coefficients in front of each one. So, such as, I could take -3 times 1, 0 plus 7 over 5 times 0, 1. And we shouldn't leave it like that, by the way. That's technically a linear combination. But we should combine these things, right? So let's do our scalar multiplication and vector addition operations that we learned way back. And what would this be? -3, 0, right? If I multiply the -3 times each of those components, I multiply the 7/5 times each of these components, we get 0, 7/5. And if I add those together, -3 and then 7/5. So this vector right here, -3, 7/5, is in the span of S because, well, I didn't really call it S. I didn't give it a name. It's in the span of 1, 0, 0, 1. Okay, does that make sense? Other things that we learned, other important things that we learned also, the 0 vector is in that span. Why is that? Just let k1 be 0 and k2 equals 0. All right, if these numbers in front of the vectors, instead of -3 and 7/5, were both 0, then of course you'd get the vector of both zeros. So the 0 vector is always in the span. Okay, so in fact, this one's pretty interesting. This span right here, if you think about it for a second, I could have changed the -3 and the 7/5 to anything I wanted to. So it turns out we can produce, using this span, any vector we want to. Any two-dimensional vector, which is what we call R2, right? R2 is the set of all two-dimensional vectors. Okay, so just by having those two building blocks, so we would say, you can say a few things. You could just say the span of that set 1, 0, 0, 1 equals R2. That would be one way to say it. Another way to say it is you could say the set 1, 0, 0, 1 spans R2, or is a spanning set for R2. That's just another way to say it. Okay, so what should be your interpretation of that? What this essentially means is only using, let me rewrite that. So only using the two building blocks, 1, 0, and 0, 1, we can produce any vector, right? Any vector, maybe AB, where AB can be anything in R2, which is important because now we know sort of like a minimal set of building blocks in order to produce R2. If I have a set with less things, it wouldn't span R2. Okay, maybe as a comparison, let's do another example. How about this? The span of, let's just change it to, how about 1, 2, and how about 2, 4? Okay, so this is a different set. Let's talk about the span. So maybe question A would be write out some examples in that span. Okay, so, all right, so let's do that. Okay, well, I can take any k1 times the first vector plus any k2 times the second vector. So just think of any. So of course we would still have, so if they're both, if k1 and k2 are both 0, of course we still can create the 0 vector. So that's in there. That's no different than the last example. But you might be wondering, can I produce any vector in R2? Let's try a few others. Let's just try, again, let's try, let's say k1 is 3 and k2 is, say, -1. Just making up numbers here. So we'd have 3 times 1, 2 plus -1. -1 times the other vector 2, 4 would equal, that would be 3, 6 plus -2, -4. And if we add that up, you get what? 1 and 2. Okay, actually 1, 2 is already in the set. But if I chose other vectors, suppose I chose k1, other scalars, I should say, suppose k1 was 5 and k2 was 1, for example, then I would get 5 times 1, 2, plus 1 times 2, 4. If I add that up, I get 5, 10, plus 2, 4, which is 7, 14. Okay, if I start to plot all of these, right, of course we already know the 0 vector is in there. We talked about that one. The vector 1, 2 is in there. So that would be this vector here. The vector 2, 4 itself is also in there. That's here. And if I start drawing these other ones, I already drew 1, 2, but 7, 14. Maybe I should have chose some smaller scalars, but 7, 14 would basically be 7 to the right and 14 up. It would be on that same, it would be parallel. Notice that 7, 14 is parallel to 1, 2. It's 7 times 1, 2. And if I use some negative scalars, like k is -1, and k1 is -1, and k2 is -2, something like that, I'll get a vector that points down and to the left, but they'll be on that line. So you might notice that the span of these two vectors does not equal all of R2. The span of, so the span in this example is not all of R2. It's just a line. A line through the origin in R2. Okay, so you have to be careful. Not every span of two things will produce R2. In this case, the span of those two objects produced a line in R2. By the way, another thing we learned the other day is that we did learn in Monday's class that every span, no matter what you have, is a vector subspace. It's a vector space. In fact, a subspace, not only is it a vector space, it's a subspace of V, where V is whatever space the objects happen to come from. Here, V is R2, because our objects are two-dimensional vectors. Okay, so we just learned is that a line through the origin is a subspace of R2. Lines that pass through the origin are subspaces of R2. Of course, there's infinitely many lines that pass through the origin, therefore there's infinitely many subspaces of R2. Okay, so let me do another example. And that'll help me define the next concept, which is independence. Okay, let me zoom in here for a second. So this next example will use different types of objects. Or no, in fact, let's do the same types of objects, just from a different dimension. Let S be the set where the vectors are, how about this one? 1, 0, 0, and the other vector will be 0, 0, 1. I think we did one like this the other day, but I think there were two different vectors. Okay, so we know that the span of S is a vector space because all spans are vector spaces. In fact, it is a subspace of V equals. Think about this for a second. What would this be a subspace of? Well, look at the objects. These are three-dimensional vectors. So there's this set. When you span this set, you produce a collection of objects that are three-dimensional vectors, and therefore this is a subspace of R3. Okay, so the question you might wonder, though, can we produce every vector in R3? And I think if you remember the example we did the other day, you'll know this is not all of R3, okay? But it's not, unlike the first example earlier, not all of R3. Why is it not all of R3? We can't produce anything that doesn't have a zero. We can't produce anything that has a zero or a non-zero in the middle component, right? You see how both of these have a zero in the middle? Therefore, we couldn't produce a vector. We cannot create the vector 1, 1, 1 from linear combinations of 1, 0, 0 and 0, 0, 1, because no matter what scalar I put in front of those two, I'm still stuck with a 0 in the middle, and this doesn't have a 0 in the middle. It has a 1 in the middle. Okay, so if I ask the same question, so write out some examples in that span, in the span of S, then some answers would be things like, I don't know, something like -304 would be in there, because that would be where, in general we're looking at K1 times 1, 0, 0 plus K2 times 0, 0, 1. And if K1 is -3 and K2 is 4, I get this vector here. Okay, also, of course, 0, 0, 0, because that's always in there in a span, because the coefficients could both be 0, for example, or, -1/2, 0 pi is also in there, where K1 would be -1/2 and K3 is pi. Okay, so that's not too bad. And then, all right, so how about this as the next example? For comparison's sake, compare the last span to the span of the set 1, 0, 0, 0, 0, 1, and then I'm going to add a third entry, 1, 0, 1. Okay, so now this would equal all linear combinations of those three. So K1 times 1, 0, 0, plus K2 times 0, 0, 1, plus K3 times 1, 0, 1, because we're taking linear combinations of a set of three things. And again, the K1, the K2, and the K3 can be anything. Okay, so again, we could write out a few things. Maybe I'll ask two questions this time. A, write out a few things. Write out a few vectors in this span. And B, the second question is how is this span different, if at all, from the last one? The last one was the span of 1, 0, 0, 0, 0, 1, just the first two items. Okay, so let's answer A first. So just thinking about this, I could choose anything I want for the case, right? Because they're allowed to be anything. So for example, if they're all 0, I'll get the vector 0, 0, 0. What if I let them all be 1? If I let K1 equals 1, K2 equals 1, and K3 equals 1, you can do the algebra and we get, just add them all up, right? It looks like I'll get 2, 0, 2 if you add the three vectors together. And I can get a variety of other things, etc., right? I don't know, maybe I'll put a third one in, something like, if I let, say, K1 be 5, K2 is -1, and K3 is, -2, then what would I get? I would get 3, 0, 1, okay, etc. There's infinitely many different things you could produce. But what about question B? That's kind of the important one here. How is this span, how is the span of these three different from the span of just the first two? If you want, you could pause the video and think about it for a second. If this were a live class, I'd ask people for suggestions. But if you think about it for a moment and take a look at the examples of things we were able to create, I don't think they're any different than the things we could create earlier. Earlier, we could create anything that has a 0 in the middle, right? And all these still have 0 in the middle because all the vectors they come from also have 0 in the middle. So if you think about it for a moment, the answer is they are the same. In other words, that third vector, having a third building block, right? This is like, remember, you think of the elements in a span, the elements in the set that we're spanning as building blocks. That third object, that third vector in our set of building blocks, was unnecessary. Why was it unnecessary? We could create it from the first two building blocks. If you look at it, right, notice this third element, 1, 0, 1, is just the sum of the first two. So I could have built it from the other building blocks, which means it doesn't add anything to what I can create by spanning the set. So in some sense, it's redundant. Okay, so that inspires this next definition. This is kind of the whole purpose of this lecture, is this concept right here, this definition. Then we'll do more examples. by the way, we'll review this again on Friday when we have a live class, so just bear with me. So here's the definition. A set S is independent. We say a set is independent if none of the objects in S is a linear combination of the other objects in S. Okay, so let's think about that for a second. So that last set, for example, the set that we were just looking at, the set 1, 0, 0, 0, 0, 1, and then 1, 0, 1. If you just inspect it quickly, since the last object is the sum of the first two, this one is a linear combination of the first two, or the other two. Therefore, this set is not independent. Okay, because to be independent, none of the objects could be a linear combination of the others. So when it's not independent, we say it's dependent. Instead of saying not independent, we just say it's dependent. Okay, so dependent. It's dependent because of what I just said. The last object is a linear combination of the first two. Okay, so let's do another example. Is the set, let's do some polynomials. So we'll do x squared, x to the fifth, x, and how about 1 plus, sorry, not 1 plus x, I'll do negative 3x squared plus x. Okay, so this is a set. So maybe I'll say this. Given the set right here, A, what vector space do these objects come from? So what vector space is S from? We usually call that big vector space V. And B, the second question will be, is S independent or dependent? Okay, well, if you look at the objects in the set, we have an x squared. These are clearly polynomials, right? We have 4 objects in this set. Here's the first one, here's the second one, here's the third one, and here's the fourth one. They're all polynomials. So you could say these are all from the set P of all polynomials, or you could even be more precise and you could say these are all from, what's the largest power of x that we see? It looks like the fifth degree. So these are all from P5. So V would equal P5. If you do, hopefully you remember what P5 is. P5 is the set of all polynomials of degree 5 or less. We argued in the last lecture that that's a vector space. Okay, and then the other question: are these independent or dependent? Is this set independent or dependent? Well, remember the definition. If we can write any of these objects as a linear combination of the others, it'll be dependent. If we can't do that, it's independent. Well, keep in mind, you're only allowed to take linear combinations. Means you can multiply these objects by scalars and add them. You're not allowed to multiply them together. So I can't multiply an x squared times an x to get an x to the third. I can't do that. I can just multiply them by numbers and then add them. Right? If you look closely, I hope you notice that this last object here. Notice that negative 3x squared plus x is equal to negative 3 times x squared plus 0 times x to the fifth plus 1 times x, and therefore, notice this is a linear combination. This is a linear combination of the other 3. Right? Where k1 is negative 3, k2 is 0, and k3 is 1. Right? And the objects themselves are x squared, x to the fifth, and x. I didn't even need the x to the fifth. I was able to produce this last entry as a linear combination of just 2 of the others. And therefore, the entire set, S, is dependent. Okay? If I were to remove that last object, it would become an independent set. All right, let's do a couple more examples. All right, so how about this? Maybe I'll change colors, just make it easier on your eyes. All right, so let's create another set. How about T is the set 1, 0, 0, 0, 0, 1, 0, 0, and the last vector is 0, 0, 1, 0. So A, what vector space V does T come from? And then B, I'll ask some questions that should be easy for you, but because we went over them, but just to make sure, is T itself a vector subspace? Subspace of V. And C is, I'll ask another one that should be pretty easy, is the span of T a vector subspace of V? And then the last question will be, is T independent or dependent? We'll use some abbreviations. All right, so let's answer these. Maybe you could try pausing the video and answering yourself, but okay, what vector space do these vectors come from? Well, notice each one of them, just look at them. They're all vectors. How many components does each one have? 4. So they're all 4-dimensional vectors, so they all come from R4. 4-dimensional space. Some people call R4 4-dimensional space. Okay. Is T a vector space of V? Well, certainly not. Look at T itself. T is not, T by itself is not closed under addition or scalar multiplication. What do I mean by that? Well, if I add two things together, if I add the first two together, for example, if I add the first two elements in T together, what do I get? I get 1, 1, 0, 0. Well, 1, 1, 0, 0 is not in T, so T is not closed under addition. I don't even have to check the other action. It's also not closed under scalar multiplication. So that's why it's no. Is the span of T a vector subspace of V? Well, we proved a theorem on Monday that says yes, the span is every span is always a vector space. Why is that? Because when you span a set, it fills in all the linear combinations. So it includes all the things like 1, 1, 0, 0, because that's a linear combination of two of the things that are in there. You naturally get you naturally end up being closed under addition and scalar multiplication when you span a set. So those two were questions kind of that I asked on Monday. I was making sure you still remember them. So questions B and C. All right, question D, this is kind of the new one. Is this set independent or dependent? So if you take a look at it, you might notice that I don't think it's so easy this time to identify one that's a combination of the others. You might be able to make a good argument. You see how in each one, the 1 is in a different spot? The first vector is 1, 0, 0, 0. The second one has a 1 in the second spot. The third one has a 1 in the third spot. So it wouldn't be too hard to argue that there is no way to combine, for example, there's no way to combine the first two, 1, 0, 0, 0, with any scalars in front of them, 1, 0, 0, 0, and 0, 1, 0, 0. There's no way I can choose any scalars K1 and K2 to get the third one, which is 0, 0, 1, 0. Why would that be? Because if I did, I'd get my third component would be K1 times 0 plus K2 times 0, and I'm trying to get a 1 in the third component. There's no way, no matter what K1 and K2 are, they'll always multiply 0 to equal 0, and 0 plus 0 is 0, and we wouldn't get a 1 here. So it's not possible. And you could use the same argument to argue there's no way to combine any two of them to get the third one. Okay, so therefore, this set is independent. Okay, independent. So some of them you can just look at and tell if they're independent or dependent. Let's do one that's a little harder, and I'll show you how I can use a system of equations to answer the question. All right, so let me go back to a different color. So again, is this set independent or dependent? One, two, three, 4, 5, 6, 7, 8, 9. Those are our three vectors. Now I could play around with it for a while if I wanted to and try to figure out, can I, we want to know. So here's the solution. I can't immediately tell like I could in the last examples. We're trying to find out, can we combine two of these with scalars in front of them to get the third one, the other one. Okay, it's not so clear here. So it turns out we can make use of a system of equations, right? For example, I could say something like this. Another way to ask the question is, so i.e., can we find K1 times 1, 2, 3 plus K2 times 4, 5, 6 equals 7, 8, 9. Well, I don't know if you recognize this. So that's what we're asking, right? You might recognize this. This is one of the ways that we write a linear system. Remember we learned 4 ways to write a linear system, and I told you the long way to do it? Well, the quick way, this is the same as, let's switch it to one of the other 4 ways. It's the same as, put the first vector in the first column right here, the second vector in the second column, and then the augmented column will be the third vector. Or if you like seeing the K1, K2, it's like this. This is the same, this is AX equals B form, right? It's the same as this. So I'm trying to solve this system. I want to solve this for K1 and K2. Well, we know how to do that, right? We write it as an augmented matrix and then row reduce it. Sorry, that's a little messy. So, okay, let's row reduce it. So what we're trying to discover is if this matrix is if this system has a solution. If it has a solution at all, either one or infinitely many, then the set is dependent. If there's no solution, so just a recap before we do it. If we can find a solution, one or infinitely many solutions to this, then the set is dependent. If no solutions to this system, then it's independent. The set must be independent. All right? So we have yet to discover that. We have to try to solve this system. What should we do here? We want to get a 0 where the 2 is, so we'll do negative 2r1 plus r2. So our first row is still 1, 4, 7. Our second row will now be 0, negative 3, negative 14 plus 6, plus 8 is negative 6, and 3, 6, 9. What else should I do? I want to get a 0 where the 3 is, so I'll do negative 3r1 plus r3. By the way, you should be able to row reduce this on your own, so you could just pause the video, do it on your own, and see if you get the same thing I get. All right, so then what are we getting next? Our first 2 rows stay the same. We get a new third row, negative 3 times 1 plus 3 is 0. Negative 3 times 4 is negative 12 plus 6 is negative 6. Negative 3 times 7 is negative 21 plus 9 is negative 12. Well, look at that. You see how the third row is a scalar multiple of the second row? Like if I do negative 2r2 plus r3, we do get the third row is all zeros. Okay. So does all zeros mean there's infinitely many solutions? Not necessarily. We're in row echelon form now. Remember the algorithm? You count pivots, 2 pivots left, right here are the pivots, two variables, right? The variables are K1 and K2. So we have one solution. We have no contradiction also, so you have to look for that first. We don't have a contradiction. A contradiction would be like if we had 0, 0, and then if this third entry was not a 0, that would be a contradiction. There'd be no solution. And then the set would be independent. But we do have a solution. We have one solution. Now, if I wanted to know what the solution is, I could keep solving, right? I would say negative 3 K2 equals negative 6. So K2 is what, 2? And then they go to the first row tells me K1 plus 4 K2 equals 7. And then I would substitute, right? This is just back substitution. K1 plus 4 times 2 equals 7. So K1 would equal negative 1. Okay, but the point is it has a solution. So in other words, there is a linear combination. There is a linear combination of of the first two vectors, 1, 2, 3, and 4, 5, 6, that equals, or that produces 7, 8, 9. And so by the definition of independence, the set is dependent. It's not independent, so it's dependent. Okay, let's spend a couple more minutes. I'll show you a quicker way to answer questions like, is this set of vectors independent or dependent? Okay, so it's all based on the same idea, though. The same idea is by using a matrix. So let's zoom in here. So this method I'm going to mention now isn't always quicker, but it will always work. So let's say this is a technique to determine if a set of let's say vectors, let's say regular vectors from Rn, we'll learn later we can adapt it to other types of objects like polynomials and matrices. To determine if a set of vectors from Rn is independent or dependent, place each vector into a column. Columns are always vertical of a matrix. By the way, that even if you originally write the vectors horizontally, you would still put them into a column, vertically into the matrix. Then, this is pretty quick and pretty nice and easy. Not always quick, but pretty nice and easy. If the rank of that matrix, let's call that matrix A. If the rank of A equals the number of columns, then the columns are independent. The vectors that make up the columns are independent of each other, and the set would be independent. If the rank of A is less than the number of columns, by the way, the only way that would happen is if you lost if there was a column with no pivot, right, after you row reduce it. If the rank of A is less than the number of columns, then we would say the set is dependent. Okay. So let's use that tool to do a couple more examples, and that'll be it for today. If I said independent or dependent A, let's deal with the set. Let's call this S is the set -1, 1, 0, 3. The second vector is 1, 1, 1, 1, and the third vector is 1, 0, 1, 0. Okay, so to determine if they're independent or dependent, instead of dealing with what we just did with the K's and everything, let's just follow the technique that I just mentioned. The technique, I'll zoom out so you can see it. The technique we just mentioned is right here. I place them into the columns of a matrix A vertically, and then find the rank of that matrix, and then make a determination. So let's do that. So the first column of A will just be my first vector, negative 1, 1, 0, 3. The second column is 1, 1, 1, 1. The third column is 1, 0, 1, 0. I don't need to put an augmented column or anything, it's just a matrix. To find the rank of A, hope you remember this from chapter 1. Think for a second what rank means. It means the number of pivots left after we row reduce it. We need to get this matrix to row echelon form. Okay, so we'll do that. We'll do R1 plus R2. The first row doesn't change. We have a new second row though. 0, 2, 1. Our third row and fourth row stay the same. So even though you put the vectors in as columns, you're doing row operations, row by row. Alright, we're almost there. We need to get a 0 where that 3 is to get it in row echelon form, right? So I'll do 3R1 plus R3, sorry, R4. So the first row is still the same. The second row is still the same. Third row is still the same, but our new fourth row is 3 times negative 1 is negative 3 plus 3 is 0. 3 plus 1 is 4. 3 plus 0 is 3. That's it. I keep going. It's not in row echelon form yet, is it? Because the pivots are not staggered. I need to get a 0 where that 1 is. Alright, alright, so let's do it. What would that be? I guess we'll do negative 1/2 row 2 plus row 3. That'll do it. Our first row doesn't change. Our second row doesn't change. Our fourth row doesn't change. I'll put that in. A new third row will be, let's see, 0 plus 0 is 0. Negative 1/2 times 2 is negative 1 plus 1 is 0. Negative 1/2 times 1 is negative 1/2 plus 1. That's 1/2, right? There's a 1 minus 1/2. Are we in row echelon form yet? Nope. I need a 0 here. So what are we going to do? Negative 2, we'll do negative 2R2 plus R4. Sorry, I'm going so fast. Like I said, you could always just pause the video and check and make sure what I'm doing is correct. But we've all done row operations for weeks now, so I'm going to do this fast. We're doing negative 2R2 plus R4. So we'll get a new fourth row. It'll be negative 2 times 0 plus 0 is 0. Negative 2 times 2 is negative 4 plus 4 is 0. Negative 2 times 1 is negative 2 plus 3 is 1. Are we in row echelon form yet? Nope, we're not. But you might notice that these last two rows are just scalar multiples of each other. So you just do one more row operation, and you'll get a row of all zeros. Okay, but the question is, how many pivots? Now it's in row echelon form. How many pivots does it have? 3. How many columns? 3. That means that all 3 columns of the original matrix are independent, which means that the set is independent because we had 3 vectors and we got a rank of 3. They're independent. This set is independent. Okay, if we had lost the pivot, then they would be dependent. Let me ask one more question, one more like that. I'll give you another set, T. Let's make this up. So how about negative 1, 0, 3, then 1, 1, 1, and the third vector will be, so negative 1, 1, and 7. Okay, same question. Independent or dependent? Is this set independent or dependent? Okay, so here's the solution. We'll use the same solution technique. We'll create a matrix. We'll put the vectors in as columns. By the way, this, even if I had written the original vectors horizontally, which sometimes people will do to save space on a page, even if I had written them that way, you'd still create the same matrix. You would always put them in vertically, even if they were written horizontally. So we went over that before. All right, so we have to row reduce. We need row echelon form for this matrix. So we'll do some row operation. This one will go a little faster because it's only 3 by 3. So the first two rows are good. The pivots are already staggered. I'm going to do what? 3R1 plus R3. So we get a new third row. The new third row will be 0, 4. A negative 3 plus 7 is another 4. And then if we do negative 4R1 plus, negative 4R2 plus R3, the first two rows stay the same. I'm going to take negative 4 times this row and add it to this row, so we get 0 plus 0, 0, negative 4 plus 4 is 0, negative 4 plus 4 is 0. Look at that. Now it's in row echelon form. How many pivots? Just 2. The last row doesn't have a pivot because it's all 0, so there's 2 pivots. Okay, but there's 3 columns. There's 3 vectors and only 2 pivots. So because it's only 2 pivots, this set would be dependent. Okay, so that's the quick and easy way to tell if a set is independent or dependent. All right, on Friday, we'll talk about basis and dimension. We'll be able to finish that topic pretty easily on both Friday and Monday. I'll do some more examples of independence. That should be a live lecture on Zoom. I'll send the link out. All right, thanks for joining me. Also, there'll be a worksheet. I'll post a worksheet on the independent stuff. So if you have any trouble with it, send me an email or ask in class on Friday. Thank you.